So when we look at migratory birds, migratory mammals, especially waterfowl, and you look at all of the possible stressors that these species need to either respond to, change habits to, the scale of this is really daunting. And I'm not going to go through the whole suite of these. In fact, you've heard a lot about a lot of them. But I am going to focus on water quality. I'm going to touch base on sea level rise because I know that's a real hot issue with waterfowl. DU has taken it on, and I got to give DU a lot of credit. It's one of the nonprofit organizations that got on board early looking at long-term strategic planning for sea level rise and climate change. And I'll finish up talking about our technology at Aquafiber. You see a lot of graphs like this, and one of the challenges I have when I teach is, you might get real optimistic when you think about trend lines of loss. But when you look at figures, 220 million acres, about 50 or a little over 50% decline, then the fact that we have declining rates of annual loss doesn't give me any comfort. Because the fact is we aren't where we were. We are 50% below just in acreage coverage. And then when you start to build that functionality question and look whether the strategic locations you need for migratory birds are there, we've got challenges that really are big scale, both temporal and spatial. And we need to be thinking big when we look at solutions. This is also similar when we look at Florida. We've had almost a 50% loss of wetlands in Florida. And when we begin to take this acreage coverage perspective, I like to go back to an old graph I used to teach with. This is 15 years old. Came out of Game and Fish. It was done initially by, I'm trying to think who it was now, and I can't even remember where this first came out. But it shows very clearly right here how regulation, this is Clean Water Act, wetland protection, can give you at least some level of decrease in decline of acreage. And I have often said, and you've heard in the last two speakers, that this functionality issue is not that simple. And so when we begin to ask the question of the remaining acres, what is the functionality? It depends. It depends on the scale. It depends on the species. It depends on what your target management restoration goals are. And those are complicated questions that are really difficult to communicate to elected officials, to funders. And so I'm going to make a pitch right here based on the last two speakers, but also on a whole week last week of Florida Ocean Alliance meeting, Florida Institute of Oceanography. We as a group, conservationist resource users, need to get back on the funding bandwagon for long-term monitoring, mapping, modeling, and we have got to get funding back at that, not just at the state level, but at the federal level. For scientists at the university going to, any NSF, for example, try to get funded for 12 years for a long-term monitoring project. Simply doesn't happen. And young investigators who come in under tenure, try to get your, committee to look at your tenure if you say, I want to monitor over the next 12 or 15-year population trends. The fact is, this is not the kind of stuff that universities are supporting, and they should. So we've got some work to do there. And if we look at water quality, and I'm going to make a case today that we have looked at water quality from the standpoint of two perceptions. It's either an engineering perspective or it's a chemistry perspective. And we haven't taken the water quality story to the same level that we've talked about when we talk about critical habitat restoration, or trophic level interactions, or energetics and bioenergetics. And when you look at impaired waters in the state of Florida, 11 million acres, 1998, fast forward to 2012, we're at 23 million. The fact is, the trend in water quality is really paralleling the trend in habitat quality and function loss. And yet, when we talk about habitats, for the most part, you very rarely hear an integration of, what is that water column looking like? So I'm going to make a case today. Water column considerations need to be at the same level as critical habitat. It's not just chemistry, it's not just hydraulics and flow, it's not just engineering, but it is looking at a three-dimensional water column that has atmospheric interaction, has sediment interaction, has wetland and land interactions, and until we take water quality to that level of discussion, we're going to miss a couple of pieces, and I'll show you a few of those this afternoon. And of course, nutrient pollution. You hear a lot about phosphorus, and I, was raised under the old paradigm. If it's fresh water, it's, worry about phosphorus. If it's marine, worry about nitrogen. That has been falling by the wayside for about a decade now, but was most recently kind of supported by the Indian River Lagoon Science Symposium, where scientists are actually finding phosphorus limitations in the north end of the lagoon, nitrogen limitations in the middle and the south. And so we can no longer look at single nutrient solutions if we want ecosystem restoration. It's a much bigger water quality picture. And you can't have blooms. And this discussion's coming up a lot. I get a lot of questions because we've got multiple sites blooming in the lagoon, including the super bloom of 2011. And you can't sustain a bloom unless the nutrients are there. And so while a bloom may not be initiated or created for that first beginning with nutrients, you can't sustain that kind of bloom if that background nutrient load isn't in place. And so clearly nutrients are part of this water quality issue, and it is, I would argue, one of the biggest challenges we face across the nation with water quality. And so when we look at this in three dimensions, and I'm not going to spend much time on this, we need to look at the water column as critical habitat. We need to look at the atmospheric deposition as part of the connection, the sediment-water interface. Very often we'll look at all of our land use issues, from the standpoint of land and water. And what really gets me a little irritated is this general concept you hear out there, especially with elected officials. Well, if we just had wetlands, the wetlands will take care of that. And I think the last presentation was very clear. Our natural wetland systems did not evolve to basically be pollutant load reduction areas. They didn't, they can't handle those kinds of high loads. And so if we're going to do wetland restoration, and we should, and land acquisition for wetland creation, which we need, the fact is wetlands alone are not going to handle the historic problem that we have in our water column and other water bodies. So then the question becomes, okay, where do we go with this? Where do we take it to the next step? Where can science help that, that issue? Two other points. We work on Lake Jesup. Just in the last couple of years, it turns out Lake Jesup is getting 36,000 pounds of phosphorus per year that wasn't accounted for in the BMAPs from groundwater. Now, nobody knows really what the natural groundwater delivery was, but I suspect, and I think a lot of people are pretty sure that, what we're doing on land, including what looked like a good thing with, reuse recharge, if you've got spray fields, they're loaded with nitrogen and phosphorus, that isn't remediated in the geological percolation, and I would argue it probably isn't in a lot of places in Florida, that those nutrients are going to get in the groundwater, and eventually they'll be expressed in surface waters. And the last big picture I want to share before I talk about aquafiber is back in 2000, 2008, range, 2009, a group of us got together. Randy Parkinson was the lead geologist who used to work with Florida Institute of Technology, and he said, we need to get on board, sea level rise. And sea level rise, and I agree, for the Everglades, it's a big system. I think that system is going to adjust because this is going to be a slow but steady process. By the way, which is not going to be mitigated by any, climate change initiatives. Our sea level rise trend for the next 50 to 100 years is pretty well set. And so we're going to live with, these projections on the conservative side of 1 foot to 1 meter, and then a number of scientists are modeling way higher than that, with lots of variability depending on ice melt, primarily in Antarctica and Greenland. But I wanted to show you something because as a marine scientist, everybody's worried about that barrier island. The focus is always east. And I gave this presentation in 2009 to NASA headquarters up in Washington, who really worried about infrastructure. And I kept saying, you know, great, let's worry about this, but watch what happens on the St. Johns River. So this is where we are today. At 1 meter, and especially look right up here. At 1 meter, you know, we do see big impacts, but you begin to see this expansion of the St. Johns in the northern end of Brevard County. As you begin to step up through 2 meters, 3 meters, 6 meters, we now have a new estuary that is the St. Johns River, and there's a lot of estuarine features, but it totally changes that landscape. And when you think about waterfowl and the needs for waterfowl, you know, I can't tell you whether over the long term this is a good thing or a bad thing, but if we are not thinking about management strategies today to mitigate some of these long-term outcomes that are on the way, then we have failed our children and our grandchildren because we just said it was too big of a problem to address. And this is where I do see a problem from both nutrients and water quality. In this northern area of the lagoon, if we just map septic systems and the likelihood that even in that foot to 1 meter that most of those, you know, low elevation septic systems fail, then you've got the potential for, you know, fairly large nutrient loads coming into surface waters. And nobody is talking about that from either an infrastructure standpoint or a climate change. So we've got lots of opportunities, lots of challenges, and I would argue that today you saw really good science, you know, based in long-term monitoring. And what we need to do is to take the things we do well, including the new technologies that allow us to model and map and monitor better, including remote sensing technologies, and start to look at these questions through a new set of lenses. And that is, number one, how do we protect what we already have? How do we restore all that's already damaged? And then how do we manage with some adaptive strategy that gives us resiliency in those natural, and I would argue, human-built systems? And so when you look for adaptive management, I think there's an opportunity for technology. And so what I'd like to do is to show you what our company, Aquafiber Technologies, is doing for dual nutrient remediation strategy. We have just began to go public in the last 2 months with 4 years of data. So I want to show you some of the results. Our history is typical of most startup companies. We began with an idea. We began with a group of really visionary investors, all private angel investors. And from 2000 to about 2006, 2007, company was focused on periphyte flowways. And with periphyte flowways, recognized pretty early, you know, work really good when they're working, but they're really hard to manage and keep them working through the variable climate and water quality changes that we see in Florida. We developed a discovery in 2007, 2008 we call aqualutions. It's a different approach. Some of you are going to ask me, how does it work? I'm not at liberty to discuss the intellectual property side, but if you think about how you might remediate nutrients, you got chemical, you got biological, you have mechanical processes, my answer will be yes. What we've tried to do is to layer technologies through a suite of patents and trade secrets to come up with a cost-efficient and highly effective dual nutrient remediation strategy. And we entered into a contract with the Water Management District, St. Johns River Water Management District, with this concept. You know, we believe we had good efficiencies, TPTN. We want it to be scalable. We wanted it to be adaptive. We wanted a small land footprint, and we wanted to keep the cost down. And this is a small scale example of what we can do. Biomass is our waste, but we can get clean water down below 5 parts, 5 milligrams per liter, which is close to drinking water standard for total suspended solids, and significant nutrient reductions. We also thought, well, there needs to be a process. If we're coming in with a new technology, we need to be thinking about how we can make you as the citizenry, the the users of the environment, our stakeholders, as well as our potential clients, comfortable with thought process. So we developed an iterative process that begins in the laboratory, moves to a mobile unit that can demonstrate and model what a facility might look like, and actually do it real time, on the water body in question. Because what we found is what I think most of us who are on the water a lot, there's no lake that's exactly the same. There's no estuary. You can't say, well, if it worked on Lake Harney, it's going to work on Lake Monroe. Or if it worked in the Everglades, it's going to work in Falls Lake in North Carolina. These systems are unique, both chemically, geologically, and land use patterns. And only once we get through this aquanite, we call it, system, can we move to actually look to tell you what a facility might look like and what it would model for possible performance. By the way, we've had this facility now in Hawaii looking at biofuels. We also did some studies in Caloosahatchee, which I won't show today, but had great results both in TPTN reduction and also dissolved organic nitrogen reduction. So we've got some preliminary results that are encouraging, but a lot of work still needs to be done. So we entered into a contract with the Water Management District, and it was a unique contract. We were the only entity actually to come in and put a bid in for this contract because it was pay per performance. You were coming in on your own nickel at your own risk, and these were the criteria the district, St. John's, wanted. Sustainable, reliable, cost-effective. Can you get to a metric ton of TP per year? And could you theoretically or model these kind of removal rates? And so what made this unique is this cost relationship. This was an invested, funded facility that our investors built, $3.5 million, in fact, in capital expense, with no guarantee of extension and no guarantee that it was going to work. Over the last 4 years, we've probably invested close to $6 million in R&D at the facility. And the idea was if the process and facility failed, you don't pay us. And so in this contract, there was a fixed $227 per pound, which was set by the district. This is not market rate, trust me. And we just said, look, we're going to take that risk because it's the only way we'll be able to penetrate the market, prove technology, prove safety, and do it at a commercial scale. And so we have gone through, we're in year 4 of 5, and I'm going to show you the data. This is where we're located. It's a small site. We're leasing property from the Water Management District. Lake Jessup is 10,000 acres. It flows into the middle St. John's. Harney and Monroe are, the most adjacent lakes. I'm going to show you a little BMAP challenge in a minute. And the size of our facility is maximum with our CUP at 7.5 million. 7.5 million gallons a day will not clean up Lake Jessup, but it gives us a scale where we can scale and begin to model how big of a system might be used over a certain amount of time to begin to see, large whole water body restoration. Water comes in from pipes 2,200 feet out in the lake, come through a treatment system, through a secondary area of treatment, runs down through to a holding pond, and then sheet flows out this marsh and literally out through right along that channel. Lake Jessup, because of 417, really has 2 complicated circulation basins. And what has shocked me as a Marine guy is that in 2010, we actually had a stage up from the St. John's that brought a significant amount of estuarine water into the system, and we were seeing horseshoe crabs, right in here. And so it's, those are the things that technology needs to be adaptive to. You're going to have daily changes, seasonal, weather changes, climate changes. Can the technology work throughout this variable relationship that we have with just our climate and our weather patterns? To date, we've flowed 5.3 billion gallons through this system. We take water quality every hour, composite it on a weekly basis, and send it out for analysis on a weekly basis for nitrogen, for phosphorus. We've got TSS meters that are literally taking data every 6 seconds. And what really was important to us is the Water Management District. This was a phosphorus-only contract. set up their own water quality testing for phosphorus. So we have independent verification of our phosphorus numbers. Being a marine guy, it took me a lot to get our investors and my boss to agree to pay for nitrogen, but we have 4 years of nitrogen data, because they were willing to trust me that nitrogen was coming online. I wish we had done a few other parameters, but we've got some great nitrogen data. So if you look at total suspended solids, you can see how variable the lake is. It kind of reminds me of any lake in Florida. Average TSS coming in is 53.8 milligrams per liter. Average going out after our treatment is 10.22. And these data over the 4 years, it's the good, the bad, and the ugly. This is when we were testing, when we were trying to force the system into failure. And so I haven't teased data out to look good. This is everything for 4 years. You're seeing the averages. TSS removal efficiency, 75.6, with, I think, pretty tight variability. And then this lake, and this tells it all. We've seen TSS at 8 and then higher than 200. We cap out at 200. And that can change within an hour with wind events. And it goes to show in these shallow lakes with high nutrient loads and lots of detrital muck, how fast turbidity can happen in a system in wind-driven events. If you look at total phosphorus, total nitrogen, this is over the 4 years. Average TP concentration coming in is 168 parts per billion. That's almost exactly the 10-year average, that we see historically. Our post-treatment, 0.03, so we are getting close to achieving or more than achieving numeric nutrient criteria, whether it's DEPs, or the EPAs. And our average removal, 72.4%. TN is a tricky little combo, for removal, and we are struggling to get our numbers. We would like to see, much higher numbers, and I'll tell you what they are in a minute, but we were looking for 65% nitrogen on average, 3.6 milligrams per liter coming in, 1.7 going out, not quite to NNCs, 47%, but this is on average. Optimize this system. We're at 93% removal. You can see the concentrations, 65% when we're at optimal right now, and we're still working to improve those numbers. I'm going to get close on time here, and I want to leave some time for questions. But here's the disconnect. When you look at BMAPs, Lake Jesup, the BMAP only regulates phosphorus. You go up to Harney and Monroe, they actually have phosphorus and nitrogen targets for Lake Jesup. They have both nutrients for their own BMAPs. And so there's a disconnect about downstream impacts that has got to be resolved. And we are headed to a dual nutrient remediation need. And I think everybody understands that you cannot get system restoration unless you look at the whole nutrient suite. We've gotten buy-off from DEP that were not harmful, that were successful, and a paradigm shift in, I think, 20 years of policy is they've given us one-to-one credit for in-lake legacy load reduction under the BMAP. Now, how that relates to stakeholders, we're working on that right now. Just a couple more. Our biomass began as a problem, now looks at a huge opportunity. I'm not going to spend any time on this other than to say we already know from agricultural tests this may be a wonderful soil amendment. We have taken this biomass, and we have a lot of it, 10 million wet pounds right now in storage. We've taken it to welding hydrogen gas. We've taken it to certified JP8 jet fuel. And here's another place where we can all work together. If you look at technology development for water quality, water quantity, and I would argue even wetland restoration technologies, who owns that at the federal level and the state level? Nobody. But yet, if you look at energy, we've got DARPA, the Defense Advanced Research Projects, looking at technology development, starting to begin to look at commercialization. We have ARPA-E for energy specifically. We need that same kind of funding. And my guess at the federal level, it should be at either EPA or NOAA or both, to start to push technology, both in the remote sensing, the monitoring, mapping area, but also in technology development. So my last 2 slides. We have multiple benefits. We've proven them, not just phosphorus and nitrogen, but we also take out RCRA metals. If it's in the water column, moving up through that, trophic level interaction, we are really harvesting a bioremediation that naturally occurs when you have over-eutrophication. We have DO improvement, habitat improvement, and we have generated a suite of, I think, 4-year databases that support exactly where the Water Management District hoped we would go. And the next step is, what happens next now that we've proven technology, and we're working with our partner at the district, be able to talk to stakeholders. But first, foremost, and most important, technology is not a substitute for natural wetland conservation, protection, and management. It's like if you had a bacterial infection, you take an antibiotic to get over the hump, and then you don't need it, your system will recover. We don't see our technology as a permanent, hard, industry component of every lake or every watershed. You get in there, you set some metrics on water quality, you hit the metrics, and either you back off and just do some maintenance, or you move to the next lake that needs it, and hope that all of other restoration strategies and conservation allow that system to kind of recheck its balance over the long haul.